Welcome to the second Combustion Webinar given by Professor C.K. Law. And I'm Peng Zhao from Oakland University. I'm a former student of Professor Law, and because Professor Fei Qi from Shanghai Jiaotong University cannot present in today's seminar, and I will take the honor to introduce Professor Law. So Professor Law received his PhD from the University of California, San Diego in 1973. And currently is a Robert Goddard Professor at Princeton University and a founding director of the Center for Combustion Energy at Tsinghua University. His research interests are in combustion, propulsion, heat and mass transfer, energy, alternative fuels, and environment. He has published over 550 journal papers with an SCI H index of over 70 and has received a number of professional awards. He is a member of the U.S. National Academy of Engineering, a fellow of the American Academy of Arts and Sciences, the American Association for the Advancement of Science, the American Society of Mechanical Engineers, and American Institute of Aeronautics and Astronautics, the American Physical Society, and the Combustion Institute. He's also a former president of the Combustion Institute. And I will also be happy to collect any questions from you during the webinar, and I will forward to our speaker at the end of the talk. So now let's welcome Professor Law to give the talk.
All right. Yeah, thank you very much, Peng, for the nice introduction. And I also want to thank Professor Yiguan Zhu and the organizers for inviting me to give this talk. So let's see, it's a challenge, especially after the talk of Professor Katharina Kozel-Hornhaus last week. Her talk is so inspirational and so dynamic. I hope my talk is equally inspirational, but on a different sort of way. She has a very broad viewpoint of the global activities and how we think. What I want to do is, in terms of inspirational, is going back to the very basics, because I've been locked down for the past few weeks, and I've been thinking more on the basic aspect of doing research, in a sense. So I have picked this topic, okay, on the rational parametric interpretation of some combustion phenomena. All right, so let's see. Let's go at it. And I did say it's COVID-19 induced. I was thinking of inspired combustion webinar, but probably induced is better for that. All right. So the key message is the following. All right? Let me just sort of read this to you. I think it's important. The reporting and understanding of scientific phenomena are frequently communicated through the relation between input and response parameters. So therefore, the communication could be inadvertently biased or misleading when such parameters are either inappropriate or not optimal. The second message is that when we interpret an observed or calculated result, a key process and or its quantifying parameters may be missed, again leading to either biased or incomplete understanding. So the ultimate is the following. This bias, if the bias is quantitative, sometimes it's okay. It's off by 20%, even off by 100%, it's okay. But if it's qualitative, then it's terrible. If the trend is going opposite, then it's unacceptable, okay? So those are the messages I want to give you right away, and those will be the message which guides my preparation of this talk. So there's a whole list of things, and I'll try to cover them all. If when the time comes, I can't cover them all, you just go to the web and then look at what I have. Different topics, okay? Definition of equivalence ratio, molecularity versus reaction order, role of the density in diffusive and convective transport, and role of controlling kinetics, in which I'll talk about two things. One is homogeneous versus flame-based diffusive system. The other is actually quite well known to many people, hydrogen kinetics in CO oxidation. Then I talk more in terms of the structure and controlling parameters in premixed flames, all right? In terms of premixed flame propagation, speed, the flux and the thickness, and the flame stretch effects and unbalanced diffusion. And finally, I talk about morphology in terms of droplet diffusion flames, the issues of sphericity and the size of a flame, how it behaves. I hope it's interesting to you. It's certainly interesting to me. Okay, let me go to the first major part, the rational identification of system parameters. Okay, let's talk about equivalence ratio. This figure, the top figure must be very familiar to you, okay? A plot of the adiabatic flame temperature versus the equivalence ratio. All right, now, right away, we look at the equivalence ratio, fuel over air and the fuel air stoichiometric. Then you can see for the fuel link case, it's between 0, the phi is between 0 and 1. For the fuel rich case, it's 1 to infinity. Well, then right away you see this asymmetry, right? This is 1, the range is 1, this range is infinity a lot. All right, so that's this way it is. And then later we see why it's bothering to us. But then the way you see it, there's no reason to get the fuel on this side and oxidize on the other side. Why don't you go the other way, right? They should be sort of equal weight. So then the way to have a more fairer prescription is normalize equivalent. You normalize it like this, okay? Then you have the fuel link is 0 to half and the fuel rich half to 1. Now, actually, it's rather interesting. If you fold this figure along half line, they actually overlap with each other. So the link and rich, they are sort of have equal significance. Now, what is the message? The message is the following. For a substantially different slopes and the ranges could lead to biased interpretation, okay, on the system responses to link and rich mixtures. This seems move rather rapidly and it moves rather gently. So let me give a more specific. It's on laminar flame speed. People over all the ages have been measuring laminar flame speed, and this is the plot. Okay, we have plotted just some representative ones, but you can see the plot of the equivalence ratio. All right, you can see on the link side, or mostly on this side, the agreement between theory, all the experiments, and the theory is very good, very tight. Whereas on the rich side or beyond this side, it's very scattered. Okay, this way. And also you can see the agreement is very good for the lower flame speed as compared to the higher flame speed. So two things, okay? So then for you to look at it, then you say, wow, this is significant. Something wrong, not too good with rich chemistry. Okay, let me write a proposal to my program manager, say, let me study rich chemistry. That's a lot of bugs there. We need to figure it out. However, I've just advertised to you that there's no really presence for link and rich, right? So what if I plot, instead of fuel to air, I flip the symmetry, air to fuel. So this is how I flip it, okay? So now this side is rich and this side is link. And then you see it's interesting. Now the rich side seems to agree very well, very tight. And rich side is all scattered. All right. So why is it? The reason is actually very simple. When you plot it between 0 to 1, the range is very narrow. So they all got bunched up here. You don't see the scatter. And when you plot it all spread out, you see a lot of scatter. All right. So then let's see that then, okay, then we go to then why don't we do the normalized equivalence ratio, okay? 0 to half and half to 1. Once you plot this, then you got as much scatter here as much scatter here, all right? So there's nothing special with the link versus rich case. Link or rich can be equally good or equally bad, all right? Okay, so that's one resolution. The other one is with this flame speed, right? The flame speed, as we say, let's go to the next one. It seems that it agrees sort of better on the lower value and on the higher value. But remember now, the scatter here is the absolute flame speed scatter, okay? And the value of the flame speed is very large. So what we need to do is plot the normalized one, okay? You have to scale the scatter, the actual value relative to the actual value. If you do that, you know, you divide it by the one, then you see actually the agreement is actually much better, closer around this maximum value. And the scatter is much bigger here because, you know, the value is very small. So the scatter also, even it's small, but relative to the actual value is very large, okay? So it's in, you know, afterthought, it's very obvious, but I just wanted to point out to you. Okay, so an interesting question. Are there, it's a homework problem for the students, are there other non-dimensional numbers in science that could be considered on normalized basis, especially if the phenomena traverses the crossover state? If you look at, go back to check your textbooks, there's a lot of non-dimensional numbers, but it's always the ratio of one to the other, all right? They do it so that they can separate out the governing equations, that some terms are important, got eliminated, things like that. But that could, certain times when you plot it, could give you a biased thinking. All right, let me go to the second topic. Molecularity versus reaction order. Law of mass action, I give this one. Basically, reaction rate is proportional to the concentrations, okay? Reaction concentrations, and this exponent here is called molecularity. This is at the elementary level, the two molecules, three molecules, they hit each other. How many molecules hit? Now, frequently, of course, for simplicity, we assume a sequence of reactions, which can be lumped into a single one-step overall reaction. For example, fuel to oxidize going this way. So then you describe it through an overall behavior, and then with an exponent here. So exponent is a reaction order, okay? Not the molecularity, it's some kind of global value, and it's almost empirical in nature, all right? And then particularly, it proportional to the pressure to the n, all right? That's an important point I want to say, so remember P to the n. Okay, so a well-known example is the Lindman theory of unimolecular reactions. You can see that the rate coefficients as a function of pressure, it goes this way, okay? It can go this way. Basically, what it says is that unimolecular reaction, when it's R going to P, is actually the high pressure limit of a second order reaction, okay? R to the M going to P to the M. So actually, it varies between 1 and 2, the reaction order. So anywhere between 1 and 2, you know, it can happen. All right, so that's a message for this one. That's a well-known example. Now, a more subtle example is the following. It's a second limit chemistry of hydrogen oxygen. I'm using this just for example. This is the hydrogen oxygen explosion limit plot, right? You probably all know that. This is the temperature, this is the pressure, and then it's a C curve. Okay, as you increase for given temperature, you increase the pressure. No explosion, explosion, no explosion, explosion. So let's look at just around the second limit, okay? The initiation reaction is H2 plus O2 going to this one. The molecularity is 2, okay? There are two molecules. Now, this is a general actually initiation. The second limit chemistry is got the branching and carrying. It's this three reactions. They are all second order. All right. Now, there's a third order reaction. It's termination. H plus O2 plus M going to HO2 plus M. Now, I purposely put this as green and put this as red. There's a reason I do that. If you just superficially look at this, and from what I said just then with the Lindman mechanism, you say, well, the reaction order should be some kind of the average between 2 and 3. If you allow for Lindman mechanism, maybe 1 to 3, okay? So just something between 1 to 3. So you do your experiment, you measure something with 2.35, you go to see your supervisor, say, Professor Ju, I got a reaction order through 2.35, and Professor Ju is very smart. He said, no, you're wrong. Obviously, I don't even need to think, okay? Why is it so? The reason is I just mentioned this to you here. The reason is that these two reactions, they are moving forward. Let me still go to, they are progressive, okay, carrying. The three-body termination reaction is inhibiting, it's retarding, okay? So the global reaction is not between 1 and 3, because this guy, the third order reaction, has a negative influence on your reaction order, okay? So your carrying and branching reaction between 1 and 2, your third order, you will bring the value down from 2. It will not make it bigger than 2, okay? So the reaction, so it has a negative influence. So overall reaction order should be less than 2, okay? It should not be less than 3, okay? So 2 and 3 is not forbidden, okay? And in particular, this negative influence can be so strong, it can push it down even beyond 1, can go to 0, okay? So that's the message here. I'm going to show you some results. So it's between 0 to 2, not above 2. Now, however, this, of course, when your pressure really goes very high, I mentioned the second order, when you go to the third order, then this HO2 will reactivate, okay, reactivate. Then through this kind of reactions, most of you probably know what I'm talking about, HO2 plus H2, then the third order reaction would come back alive. So, but that's only above, say, the second limit and things when the pressure gets really, really high. Then you get to third order. So in general, then you expect the reaction order can go from 2 when the pressure is low. Then as the pressure goes higher, it can decrease, could approach to 0. And then the increase again, go from 2, can go to 3. Now, let me show you the reaction order that's extracted off from the laminar flame speed, okay? You get a laminar spring, you can extract out of that. Overall reaction order as a function of pressure. Look at the case of phi equal to 1 equal. I still use the regular equivalence ratio, okay? It's just old habits, right? Otherwise, also, if I use the normalized one, people don't know what I'm talking about. So anyway, phi equal to 1, you can see that when it's very low, it's close to 2, basically 2. And then as pressure increases, goes down, going to here. Now, when it's very lean, it's really significant. When it's very lean, the branching reaction is not that significant. Temperature is low, but termination reaction, three-body termination reaction is not, that doesn't depend on pressure. So its influence is big. So it really brings the reaction order down, all the way from 2 to 0, even less than 0. Okay? And then when the pressure goes up, it goes back up again. Goes approaching 2, and then if there's only 100 atmosphere, you can do more, and then it could go higher. All right. So just remember the reaction order can vary all over the place also, and depend on pressure and depends on the equivalence ratio, or all of this. All right. So chemistry is not in a sense, not trivial, but those reaction order is not constant. Awesome. All right. Okay. Now let me talk about the role of density now in transported quantities. So again, I just want to show you something very sort of trivial, obvious to you. Just governing equations, simplified governing, mass diffusion, just for illustration, mass conservation. You have seen this, rho and didal rho v and rho d equal to this. All right. Transition term, convection term, diffusion term, reaction term. The message I want to give to you is the following. You look at the convection term here. The coefficient here ahead of it is rho v. All right. For the diffusion term, the coefficient here is rho d. All right. Okay, come back to here, rho v. Now, frequently when you see governing equations, you just have the v. The rho takes out because certain times, frequently, people in fluid mechanics, they treat as constant density, right? In compressible flow, you take out the rho. But don't take out the rho because we're in combustion first. All right, density varies. But even more so, the message I want to give to you is that this represents the transport of sort of the kinetic energy, basically momentum transport, basically, okay? Momentum transport is not V, it's rho V, right? Remember Newton's second law of motion? It's not the, MA, it's change of rate of change of momentum. It's rho V, it's not V. So rho V should come together. Always think of rho V together. Don't think of V, rho V, okay? And, okay, the second point is D. Diffusion coefficient is not just to describe this, it's rho D, not D, okay? Let me elaborate this further. You look at the transport coefficients, mass diffusion coefficient, this transport equation, given diffusivity going by viscous. Viscosity coefficient, right, for the viscous is mu over dV dy is given by this. Thermal conductivity is with this coefficient. All right, look at these three coefficients. They basically have the same form. Of course, they're from kinetic theory of gases, molecular transport, collisions. They're the same form. However, for the diffusion coefficient, there's a little bit different compared to that. There's a rho here. The other guys don't have a rho. So then say, why so odd? It's got a rho here. But the other way is say that that's something not right. I really should not define this guy as rho. I should move the rho to here. It should be rho D. Then everything should be symmetrical. Okay? So that's the sort of haha moment you kind of recognize. So therefore, the transport coefficients should be the proper way so that they are of equal or kind of significance, should be lambda, thermal conductivity, mu, viscosity coefficient, and rho D. Okay, they are density and therefore pressure insensitive. Okay, they're density insensitive. If you just have the D, it's not. So rho D instead of D is the proper diffusion coefficient. That's the way you always look at it. Now, of course, we have also studied diffusivities, right? Diffusivity will be, of course, D, and then you have the kinematic viscosity. Kinematic viscosity is mu over rho. Thermal diffusivity. They are derived quantities. They are the viscosity transport coefficient divided by the rho. All right, so they are not the elementary, fundamental. They are derived one. They have some meaning. They got the unit of length square versus time, print something, but they are pressure dependent. Therefore, density dependent. Okay. So, okay, here give another sort of simple message I want to give. Interpretation of non-dimensional number. It's all related. So, interpretation of non-dimensional numbers. You look at Lewis number, lambda over Cp rho. How do you interpret it? We always say it's thermal diffusion versus mass diffusion. So you should interpret it as lambda over Cp over rho d, okay? You do not bring the rho up here and put the d here and interpret it as this way, all right? You interpret this way, it's okay, you can do whatever you want, but then when you want to systematically do some vary some parameters, you don't vary this way. You try to vary this way, okay? By the same reason, for the Reynolds number, okay? Everybody knows Reynolds number, rho u L over mu. Now, the proper way to interpret it, we all know, right? Reynolds number, inertial force, inertia to the viscosity. It's the momentum. So the numerator is rho u. That should come together. The denominator should be mu over rho. Don't bring the rho down here to get this way. Don't try, well, I shouldn't say don't, but then when you do that, you have to be careful. Don't do this way. You know, you vary the u to vary the inertial force for your Reynolds number, you vary the nu. You should vary this way, consider, okay? All right, so now let me go to this, the rho u issue. This then leads me to talk about the laminar flames, all right? So here, let me just very quickly do a very, very elementary derivation for the laminar flame speed. And you know the laminar premixed flame, you know, the basic structure, right? The preheat zone, the reaction zone, and the downstream. Now, first thing you recognize in this problem, The conserved quantity, the mass quantity, is the flux, is rho u. Okay, rho u coming in here. All right. So if you sit at the flame here, you see what's the velocity approaching it. It's not just the flame speed SU, it's rho u. It's rho SU. All right. Okay. So the first thing remember, it's rho SU, flux. That is the conserved quantity, not the flame speed, not the SU. All right. Okay. Let's do a quick derivation. If you do a balance in this region, convection diffusion balance, it's this term, okay? And then this term, and then if you just cancel out the d by dx, basically F.
摸得很爽啊！
Okay, yeah. Oh, so if F
在干
0,
嘛？
then we'll go with the lambda over Cp of d over dx. So the flame flux, flame burning would be lambda over Cp over the thickness. Okay, lambda over Cp. Again, look at it. Lambda over Cp now. Okay, see that? Another balance. Then we have overall mass flux balance. Whatever the reactants coming in here will be reacted. Okay, so the thing that enters, I'm seeing the cursor here, will be the, so the balance with this one would be F naught going to the reaction rate going to L R. So anyway, I have obtained two relations. With this balance, I get this two, and with this balance, I get this one. I can only obtain two independent relations because I only have two independent processes. For this frame, I have two, diffusion process and reaction process. I only have two processes, two characteristic times. So I can only determine two quantities. Okay, just two. I can only have only two relations. That's all. You cannot get more. So from these two relations, I can determine two quantities, namely the flux and the thickness. Okay. So I can solve for them. You know, I have two quantities. I can multiply them. I get one quantity. I divide them. I get another quantity. That's all. That's all the information you can have. You cannot milk out any more information from this. So let's look at it. You have the flux square over lambda of Cp this way. Salvage number is the ratio of the flame thickness. Okay. So let's don't worry about that first. You get this one. And the flame thickness is this one. Okay. Another message I want to give to you. We always say, I think I'm repeating, we always say the eigenvalue for laminar flame propagation is the flame speed. Okay. It's not just the flame speed. The laminar flame propagation has two eigenvalues. One is the flame speed or the flame flux, the other the flame thickness. Flame thickness by itself is an eigenvalue of your flame. You have two eigenvalues. Why you have two eigenvalues? Because you have two processes, right? Diffusion and reaction. So you got two eigenvalues. Okay, so that's one. All right, then let's look at this guy. You look at this guy, you see this is lambda over Cp over W. Lambda over Cw. Now, I've just advertised to you that lambda over Cp is pressure insensitive. So therefore, this F only depends on in terms of pressure, only depends on the reaction rate. Similarly, this one, the thickness, the sensitivity to pressure is only through the reaction rate. Okay, it's not through the lambda over Cp, not through the diffusivities. So let's look at this now. The dependence on pressure. So the reaction rate depends on pressure to the P to the N. This one is pressure insensitive. So the flux will go with reaction rate to the half will be P to the N over 2. Okay? Now, the thickness also go to 1 over reaction, so P to the minus N over 2. Okay, that's dependent. And the laminar flame speed. So here's the question. Laminar flame speed is F over rho U, right? I told you it's rho SU. And then it'll be P N over 2 minus 1. Okay, remember this relation. Okay, so now what's so special about it? I think quite a number of you have studied, you have read papers and some textbooks and all that. And they talk about the dependence of laminar flame speed on pressure and n over 2 minus 1. And then they sometimes make the statement, oh, for a second order reaction, right, n equal to 2. Of course, we all know that n is not 2. Rarely it's 2. But let's say a second order reaction is n equal to 2. Oh, then the flame speed is pressure independent. And then it sounds, it's very fancy, very, very, very significant, right? There's nothing big deal, okay? Because this is a derived quantity. The fact that its pressure independence -1, this -1 is due to the pressure density variation. It's a derived quantity. It's nothing big deal. All right. So let me just say what I said. So for n equal to 2, the laminar flame speed is not a function of pressure, but this is just a cancellation between density and reaction. This is not a fundamental result, nothing big deal. Now, also, then generally, of course, n is less than 2. For n is less than 2, right, we know that then SU will decrease with pressure and the F will increase with pressure. That's what we get. All right. So that's another thing. I'm going to show you some more results. Now, another important thing is that the flame thickness. Flame thickness varies with pressure to the minus. So as the pressure increases, the flame gets thinner. The pressure decreases, the flame gets thicker. Nothing big deal. You know that. And indeed, that is the motivation for people to do experiments under low pressure. Because when you under low pressure, the flame gets thicker, then you can put your thermocouple in, put your sampling probe in, and measure the flame. So the flame gets thicker. And then one explanation, you tell the students, whatever, or tell your friends, the flame gets thicker is because the diffusivity is smaller than it gets thicker. That is not correct. Has nothing to do with diffusivity, the flame gets thicker. The flame gets thicker because this guy, reaction rate gets slow, okay? Because the diffusivity depends, the diffusion effect depends lambda over Cp, which is not pressure sensitive, okay? So that's what you see. All right, let me show you some, so this is what I said. Let me summarize again. Dependence on the flame speed on the pressure is through chemistry and density, both. So the observed decreasing trend of flame speed with pressure is a density effect. It's not chemistry. No, it has the effect of chemistry, but it's not, the reason it decreases actually is due to density. All right. Again, some chemists, our chemistry friends, sometimes have been saying, oh, it decreases with pressure. It's because of third body termination reaction. It's a definite demonstration of third body termination reaction making it decrease. Yes, third body termination will make it, will reduce it, but it's not the reason causing it to decrease. Okay, the reason causing it to decrease is density. Okay, so if you look at this results, right? Laminar flame speed, there's calculated results for methane air. Again, equivalence ratio, I'm sorry, equivalence ratio, not the normalized one. But as you can see, if you increase pressure, it decreases. But if you plot it as the flux, rho u, then it increases with pressure. And that's a proper way, okay? Because it goes to P to the N over 2. Okay? So anyway, I hope that it's kind of obvious afterwards, but it needs to be pointed out. So that's the first part of what I want to say. The second part is the inclusion of essential processes and parameters. All right? Again, definitions and all that. The first one is really simple. Many of you know. The role of back diffusion in flames. Now, again, I'm talking about, we're comparing two systems. One is homogeneous system, all right? One is homogeneous system. If you, basically there's no diffusive transport. So you have a fuel and oxidizer move, and then it has to generate its own radical, right? So radical H and HO2 is generated from reactants, H2O2, right? Going through this reaction, generating this. However, in a diffusive system or with flames, it's diffusive system. This basically is a flame structure plot here, all right? And you have the free stream coming in here and then going here, and the temperature will go up here, okay? Now you can see the radical is produced, the radical concentration is in the middle of the flame, further downstream of the flame, at the higher end of the flame, okay? You generate the H, all right? Instead of generating H from your free stream, it's generating in your flame. And then if you look at the particular reaction, which got a lot of heat release, you know, this is a one reaction which generates the flame. And this hydrogen radical, after it's generated, then they'll back diffuse upstream, okay? Then it'll react, for example, with H plus O2 plus M, going to with this, all right? The third body termination, or it'll go to branching, okay, H plus O2, OH plus O, going to here. But whichever way, it goes forward to do this, all right? Sort of back in time, going this way. And then through that, it generates the HO2s, H2O2s here. So the production of all this kind of very important radicals actually is through the back diffusion of the hydrogen from the flame rather than going from the free stream, okay? So I have to rush a little bit. This one is really, again, trivial to you guys that I'll just briefly mention. CO, you know the CO oxidation, it needs hydrogen to do, okay? It needs hydrogen. Without the hydrogen, it just goes very, very slowly, all right? So you have to allow for the effect of hydrogen. I'm going a little bit faster. So for the explosion limits, for example, the explosion limits for CO, pressure over temperature, no explosion and explosion. If it's simply just CO, then it's the green line, monotonic decrease. But if you just put it just a little bit of hydrogen, 10 to the, I forgot what, let's see, 10 to the minus 4, 10 to the minus 5, it suddenly behaves like hydrogen. Remember the one I showed you, the hydrogen oxygen? There's this so the lower part of the C curve going up, going this way. Okay, so minute amount of hydrogen addition would takes over the explosion chemistry of CO oxidation. So you have to really know which process you're talking about. This is really hydrogen explosion, not CO. Okay, so those are the things. All right, let me talk about dynamics of stretch flames. I have about 10 minutes. I'll go a little bit faster. For stretch flames, we know that there's effect of stretch defined at d over dA 1/8 dA dt. For the stagnation flow, it is the stretch rate is bigger than 0. For the Bunsen flame, let me see, expanding spherical flame is bigger than 0, but for the Bunsen flame, it's less than 0, the stretch rate, okay? With this, that's important. Now, the important point to recognize that the straining is inherently coupled to imbalance diffusion, coupled to Lewis number. It's coupled to the Kalowitz number. It's 1 over Lewis number minus 1 times the stretch. So what does it mean? I have to go a little bit faster now. So, for example, if you see for the stagnation flow of flame, okay, if kappa is bigger than 0, then the Lewis number, if it's bigger than 1, okay, then you have more heat loss than mass gain because 1 is leaving the control volume, then the reactants absorb into the control volume. So the flame temperature and flame speed will decrease, Lewis number bigger than 1. If Lewis number is less than 1, then it will increase, okay? So for the stagnation flow. The Bunsen flame is just the opposite because the heat conduction moving forward focuses the heat. Mass diffusion defocuses the heat. So if Lewis number bigger than 1, then the T would increase and the flame speed here would decrease, okay? So you see that it's flipped. when your stretch go from from less than 0 to bigger than 0, this is decrease, but that's increase. And with this increase, that decrease. So everything goes with this Kalovitz number, okay? As it's whether it's bigger or less than 0. So this can be bigger or less than 0. That can be bigger or less than 0. So you have to recognize this, because otherwise your you interpret your results going crazy. One manifestation of this confusion, one manifestation, right, is the following. It's the determination of laminar flame speeds. If you determine laminar flame speeds, is a time-honored activity of combustion researchers. It's been doing it hundreds of years. People started measuring it in 1910 or 1920. This is the laminar flame speed for methane air, stoichiometric, as a year of publication, okay? And these are the data. You can see the data is all over the place. The data is all over the place. And they can vary a lot, the scatter, all right? What's important is that they don't converge, okay? In any branch of science, as time goes on, the accuracy will get better, they should converge, but they don't converge. What does it mean? That means there's something missing in your understanding of the problem. You're doing something wrong. People, all the people, everybody. What they don't realize at that point is that stretch can flip your behavior. So you measure with the expanding flame, positive stretch. You measure with Bunsen flame, negative stretch. They can scatter this way, that way, that way, that way. So that gives you all this, okay? So only in the mid-1980s, when the theory came out from a lot of outstanding theoreticians, and the experiment came out to say, oh, I have to take away the stretch rate, stretch effect. Then the flame speed gets converged. Right now, we still measure flame speed, okay? But then the tolerance is much tighter, okay? So why is so important? Because we need accurate determination of flame speed, which is an important input to the determination and validation of reaction mechanisms, okay? All right, so this one, I'm gonna skip it now, sorry. This is, I don't know, Zheng Xiaoling, are you here, Xiaoling Zheng? That's her, part of her thesis. Anyway, you guys can look at it. Let me talk about the last topic. It's the droplet burning, D-square law. Everybody knows D-square law in combustion studies, okay? You have a droplet here, and then the flame is surrounded by, the droplet is surrounded by a flame, okay? And the heat comes here, vaporizes the droplet, fuel vapor comes out, diffuse to the flame, and oxidizer diffuse to the flame, and then they will react, go this way. Okay, so D-square law, all right, D-square law. D-square law says that the radius square versus time is a constant. Everybody knows. And also, flame front standoff ratio. Flame front standoff ratio is the instantaneous value of the flame radius or diameter to the instantaneous value of the droplet size. Okay, this value to this value, the ratio. This ratio is a constant. Okay, flame front standoff ratio. So as the droplet burns, it gets smaller, and the flame will also get smaller. So that's the reason. Now, also, you look at the formula. I'm not showing it. You look at the formula. It says that this value, you put it typical values of hydrocarbon, it's around 40. Huge flame. All right. So that's D-square law. Now, so let's verify it. Okay, right? We are researchers. You have the theory. You do the experiment. Right away, you run into problems. The theory is spherically symmetric. How can you get a spherically symmetric flame on Earth? You cannot, because the flame is always, buoyancy will make it bigger, all right? So long time ago, Japan, people have measured, Kumagai has measured, he has reduced the buoyancy effect by doing the experiment in free fall. And as you can see, the acceleration, if the acceleration is kind of large, then the flame is elongated. When there's no free fall, then it's Ferguson. Then you can measure the flame radius. This one is nonsense, flame radius, okay? So what you see is that you experiment then shows the flame front center ratio keeps on increasing, all right? And the flame size is less than 10 rather than 40. That's a big difference. That's a big difference. So once you do realize that, then you try to understand why. So that theory is formulated. For keep on increasing is due to field vapor accumulation effect. I'm going fast now. And that one explains it well. For the flame size, let me mention this. Flame size, why the flame size is much smaller than the experimental, than the theoretical size, okay? The reason is variable property. When you formulate d-square law, you assume Lewis number equal to unity. Okay, we do that all the time. The Lewis number unity is, and they say, oh, it's one, even it's 1.1, 1.2, it's close to 1, it's good enough. Now, the trick here is the following. The controlling process for, it's heat and mass transfer, right? Heat and mass. And heat and mass transfer here. Unity Lewis number says they are the same. However, the controlling process is the heat diffusion in the inner region. The heat will go into here, vaporize the fuel. So heat diffusion in the inner region. It's mass diffusion of the oxygen to the flame here. So it's mass diffusion in the outer region. So you really should compare the heat diffusion in the inner region to mass diffusion in the outer region. Okay? So it's a mixed Lewis number because they are not the same gas. When you say Lewis number unity, you're talking about the same gas. If they are not the same gas, this is full of fuel, this is full of oxidizer and nitrogen. They're different gas. So it's a mixed Lewis number. So your Lewis number should be lambda 1 over Cp1 over rho d2, different regions, inner region, outer region. And when you put in the numbers, okay, then the flame ratio is, instead of, if it's 1, this 1, but now it's this value. So this value makes it much smaller, out of 10. So that explains it. But what I want to say again, you have to know the proper parameters. It's a mixed Lewis number, okay? All right, so almost done now. So recap, all right? So we'll talk about all this: equivalence ratio, reaction order, density, controlling kinetics, and then we talk about premixed flames, different things, and the droplet diffusion flames, all right? Okay, final one. I want to give, especially students, a lockdown activity. You're locked down at home, right? Got nothing to do. Oh, you probably got a lot of things to do. But I want you to think about this problem. Revision of the turbulent flame regime diagram. Those of you who've studied combustion, you know turbulent flames, there's turbulent flame regimes. And it's been proposed in the mid to late 80s, and it's been around all the time. It's the Bible in a sense to do that. However, a lot of understanding of premixed flame behavior has not been integrated here. The problem is the following, because this one was developed in the late 80s, late 80s, and also understanding of stretch flame behavior is also in the late 80s. And the result of the understanding of stretch flame behavior is never integrated into here. It's about time. Why is it? For example, Lewis number effect is important. It's never here, all right? Especially the strengthening and mobility of the flame. Now, we just say that stretch can increase the burning rate. The information is not here. Also, here it says that if you stretch a flame, the flame will extinguish. No, the flame, if you stretch a flame, the flame will move. The flame does not sit there to let you stretch. The flame will move away to find a place to survive. So the mobility is important, but that effect is not here. Role of flame front cellular and pulsating. When a flame propagates, expands, it develops cells. It can make the burning much faster. That effect is not here, all right? The flame can also pulsate this way, or it can form spirals. If you look at this one, it's the flame surface. It's got spirals. All those effects can make the burning different. It's not there. Also, we did not account for radiative. Radiation is inherent part of transport processes. Okay, that affects the flammability limits. Here, it's never really talked about the flame doesn't go out. The only way it goes out is due to stretch here. But radiation is a function of the flame temperature, and as such, it is part of this one. Okay, it's not there. So I don't know how to. It's been bothering me all this time. I don't know how to. You can put in a lot of X's. That's no fun. Can you somehow modify this? Put in different parameters, generalize the parameter, and then make this a regime diagram richer. So okay, so I'm a little bit over, 3 minutes over. So my final message is you have fun, even in this lockdown time. And I'll try to have fun. Okay, thank you very much. All right.
Thank you very much for the very insightful talk, Dr. Law. We do have time for 3 or 4 questions. Yes, so the first question is, these insightful examples are really important. Would Professor Law plan to update his textbook in the next edition with such thoughts?
I've been thinking, a good friend of ours, I wouldn't mention his name, he also has a book. So he told me that he is now revising his book. Okay, so the message is that never let, guys remember, never let the crisis go, you want to take advantage of the crisis. Okay, a crisis is an opportunity. So a good friend of we all know that. I'll tell Professor Zhu and you later who he is, but he is revising his book. Okay, I'm tempted to revise my book. I haven't done that yet, but it's right next to me, and I kept on thinking, yes, I do intend to do it, but I need a lot of help from my friends or from you guys too. It's a major project, but writing a book is important. Writing review papers is important. For example, Professor Zhu, he has written quite a number of review papers. His recent review paper on low temperature chemistry, that's important. Students, at the time, after maybe 10 years, after 15 years after you graduated, or 20 years, you should have enough experience, write review papers. Review papers get the knowledge propagated. It synthesizes the knowledge. It compacts the knowledge. And they get it. Now, that you want to really condense the knowledge, really compact, okay, to write a review paper. Okay, so it's a long answer to your short question. You keep on reminding me to revise my book, Professor Zhao. I'll try to do it. Maybe you can help me.
Okay. So the second question is, what is the main difference between laminar flame speed and laminar burning velocity? Many researchers use these 2 parameters interchangeably in order to represent the same quantity.
That's right. I mean, combustion is an old science. When you have old science, you get the old habits. Okay, so people use this terminology, use that terminology. They just can't change. So I guess in a sense, to me, it's the same thing. Flame speed, I think, is better because velocity has the implication of a vector quantity. Speed is scalar, right? So laminar flame speed is a scalar one, so we should use that. But I use at certain times, I go out, I go crazy, I say it's laminar burning velocity. I do that too. So just like the use of equivalence ratio, you see, I still use equivalence ratios when I publish papers, I still use, even though I believe normalized equivalence ratio is the proper way. But I still do that. Now, what can I do? So, because if you do the regular normalized equivalence, people cannot figure things out. So thanks for pointing out. I mean, you really know combustion. Okay, some more questions?
The third question is, with respect to the last frame key missing elements in the turbulent combustion regime, the Maxton length will tell how stretch and Lewis number affect flame behavior. The question is, what do you think of the concept of turbulent Maxton length?
Yeah. those are the things. Actually, if you look back, Calovis number, the parameter that controls the stretch flames is not the Calovis number itself. It's the Calovis number times the Seldovich number. Okay, it doesn't have a name yet. Okay, it's there's a Seldovich number there, and that's a general parameter because the Seldovich that number, an unknown number, it's in my textbook. You guys can see it. That number is very general. It includes the aerodynamic effect. That's the stretch. The stretch itself includes the flow non-uniformity, flame curvature, and flame flow unsteadiness, right? And it got the Lewis number there, and it got the Seldovich number. This is Seldovich number. Seldovich number, it includes the activation, it includes the adiabatic flame temperature, exothermicity. So that gets everything under the sun in there, that particular number. I think in my book I call it sigma or something, but it doesn't have a name. I suspect that Professor Zhao, that number will come into a very prominent influence. But the point I want to mention also is that when there are cases in which the burning velocity increases with stretch, all right, those concepts are not in, those concepts are just briefly described, but not thoroughly analyzed, even in laminar flame case, but definitely not in the region diagram. Remember, stretch can intensify burning, so it's not there. Good question.
Okay, so one more question, since we only have 1 minute left. So as combustion research relies more and more on quantitative measurement, detailed simulation, and detailed chemistry, what is your perspective on the future development and role of combustion theory, which is more based on the global parameters?
No, you need both. You need both in terms of simulation, because sometimes we cannot do all the experiments. We do the simulations, but of course, you know very well, simulations, garbage in, garbage out. But a lot of times, you know, we have wonderful people. They do really wonderful theory calculation, which is essential, absolutely needed. But then in terms of theory, simulation, you do quantitatively accurate. But the theory, I think there's less emphasis now, and it's regrettable. And I want to encourage the student to spend some time in there, because that one would generalize and generalize the concepts, make the concepts simpler, but equally important. Okay, it doesn't mean things which is smaller number of parameters, which is not accurate. All right, but then to do that, you really need to understand the basics. You really need to understand the basics. You know, all those reaction rates, which I talk about, reactivities, reaction order, and all that. You really have to do that. So we need people on both sides. But one not regrettable. I may be regrettable. I'm seeing sort of a little bit less emphasis on theory. All right, and but the theory is so important. Theory is absolutely important, and mathematics. There's a lot of de-emphasizing many places on mathematics, even in the lecturing, in teaching. This is not right, right? Because you need the mathematics to do the theory and to do the understanding, right? One good example is, you know, your good friend, right, Tianfeng Lu. He developed the directed relation graph through graph theory. He picked up the theory himself to do that, and then he reduced the mechanisms and all that. We need the theory, we need the mathematics, we need the computation, right? So right now, research is 3 legs. Before, research is 2 legs, experiment and theory. Now research is 3 legs, research, experiment, theory, and computation. You need 3 of them. A student, any student, I always tell you should probably know 2 of them. If you're really curious whatever, you do 3 of them, right? Professor Ju does all 3 of them, right? I'm seeing him there, and Peng, you do all of them here. So there's nothing wrong doing all of them. So that's my, again, long answer to your short question.
Okay, so due to the time limitations, I will basically combine and forward the rest of the questions to you, and then we'll try to get back to the to those who ask the questions later. Okay.
Okay. So all right, you guys
Any
keep
comments or
yeah, you guys keep well. All right, and science will go on. And again, remember, out of crisis, there's opportunities. Okay, never let a crisis go to waste. That's right. That's what the colleague said. Never let a crisis go to waste. Okay.
okay.
All right. Have fun.
Yeah, Professor Law, I think that this is Yiguang. This is a really beautiful talk, and this teach us that how to critically think about the science, right? We always take the basic concept of combustion as granted. But what your example basically shows that you can flip it over to rethink from a different side. That is how the fundamental way about how to think about research, right? Not only just combustion, but also to other fields as well.
Yeah. Yeah, that's right. I mean, you know, some of you after you graduate, you may not end up in combustion. Not a big deal. Go to some other areas. Use your mind. Use your thinking. And again, another word I didn't mention, this is science is beautiful. When you find out something really nice, you feel happy. Okay, even in this lockdown time, you feel happy. Okay, yeah. So stick with science.
Thank you.
Okay, thank you so much, Professor Chiu, for organizing this seminar.
Thank you for giving the lecture at this difficult time, and thank you very much for the strong support.